In the next lessons, we will start by taking an application that was configured for a development environment and prepare it to eventually be deployed on a Kubernetes cluster. This will be done step by step. First, you will need to tweak your application so that it can run in containers. Then, you will see how you can use containers to complement your application and run a database without even installing the actual software. Eventually, you will create a whole environment with your containers that will enable you to start all the applications with a single command. This can be very useful to share the application with your colleagues. I hope you're excited to learn about all of this. If you're ever blocked, if you need any help, or even just to say hi, you can easily get in touch with me via Twitter. My handle is Joel__Lord. Yes, there's 2 underscores there, and I usually answer back pretty rapidly. My DMs are always open if you need to get in touch. Before you get started, you will need a few things. First, the application is built with Node.js. It will be useful, but not necessary to have Node.js installed on your machine, so you can test everything locally. If you don't have Node.js installed, don't worry, you won't be able to run the application locally, but as you learn more about containers, you will see how you can use those to run the application without actually installing Node.js. If you want to install Node, you can go to nodejs.org to find the installation instructions for your operating system. Speaking of operating system, I'm using a macOS system on my machine. The instruction that will show will work both on Linux and macOS, but might not always work on Windows. I will assume that you have the necessary knowledge about your operating system command line tools to be able to navigate the folder structure and copy files around. You shouldn't need more than that. Next, you will need a container runtime. The examples in this course will be using Docker, so you will need to install it for your operating system. Installation instructions can be found at docker.com. If you're using a Linux-based operating system, you can also use Podman instead, which is a little faster than Docker. You can find more information on Podman at podman.io. If you choose to use the latter, you can create an alias with the command alias docker equals podman, so you can still use the exact same instructions that will be specified in this course. Podman uses the exact same syntax as Docker, which makes it easy to switch from one to the other. In order to download the source code of this application, it will be useful to have Git installed on your machine. You can find out more about Git at git-scm.com. Finally, this application will use Giphy as a source of random images. Now, I don't want to exceed my daily quota of random GIFs, so you will need to use your own API key. You can find out how to do so by going to developer.giphy.com and then click on the Get Started button. From there, follow the instructions to create your first application and to get your API key. If you don't want to install those tools, there is a container that has all the tooling necessary that was already created for you to use. The only thing you will need to get this started is Docker. If you have Docker installed, you can use the command in the tools/course-env.sh file to start the container with all the tools installed. You will even be able to run Docker from within this container. That's all you need for now. You're ready to get started and to explore the wonderful world of containers. The application we will look at today is an application that will render GIFs from Giphy and add a caption to it. This application is entirely built with JavaScript. It has a Node.js backend and a Vue.js frontend. The application UI is simple. It asks for a keyword. It will search and display a random GIF from Giphy. Once you are satisfied with the image, you'll be able to add a caption to it. The server will deconstruct the GIF frames, add the caption, and recreate the GIF for you. Everything is then saved to a database so that all the users can benefit from your creations. Seems nice, right? Let's start building our application. First, let's clone the Git repository that contains all of our code. This can be done through your terminal by cloning github.com/joelord/kates-course.git. Once the repository is cloned, you can cd into that directory. In here, you should now have 3 folders. one for the front end, one for the back end, and one for your database. Let's go into our front end. From here, we can run npm install. That would install all the required dependencies for our front end. Once this is done, you can run npm or run serve. This will start the Vue.js application. As you can see, my application is now running at localhost 8080. I can go to my browser, open up a new tab, go to localhost 8080, and I can see the application here. So we've got animated meme generator, but nothing works for now. That's because we don't have a server started yet. So before we get started with our server, let's just go to Giphy developers. From here, you can click on Get Started. You can log into your account. From inside your account, you can create an application. Just use the SDK here. Use the next step. Let's start by giving it a name. We'll call it Kubernetes course. And the description will be course from Joel Lord on Egghead. We can check everything, create the application, and you should have your API key here. So go ahead, copy that API key, and go back to your terminal. In here, I'll open up a new tab, and I'll move from my front end to the back end. You can see here that I have a file called API keys, so let's open up a code editor. I can open up API keys, and in here, I will paste in the API key that I just got from Giphy. Once this is done, you'll be ready to get started with the server. You can start the server by running npm install to install all of the required dependencies, and then use node dot to start the index.js file. Our server is now running. The Node.js backend has a health route that was built in by the team that had built this application. It can provide you with the status of your API. It checks the status of the server and the database and returns a status and a timestamp. So let's open up a new tab here, and let's try to do a curl to localhost 3000/help. You can see here that we have an error. It says that connection is refused. You can dig into the error trace to see where this error originates from. But you will notice that this error comes from the fact that we don't have a MySQL server running. Our application requires a connection to the database to list the previous GIF creations from the visitors of this website. Without running a database, nothing works. So how can we start a database without spending too much time configuring the said database? This is where our containers will come to help us. Before you spin up your first container, let's take a quick look at what a container is. In this course, I will be using Docker for most of my container management. Docker is simply one of the tools that can be used to run containers. I usually like to use Podman as my container engine, but it's only available for Linux right now. Docker comes with a virtual machine that will let you run containers in any operating system. But it's interesting to note that they are both 100% equivalent, and each command I will be showing here will also work on Podman should you decide to use that alternative instead. So what is a container exactly? Well, you can think of a container as a way to package up all of an application, its source code, its configuration, and everything else it needs to run into one single package. Essentially, imagine a big zip file that would contain your source code or executable, along with all the applications required to run it. This way, instead of shipping your source code, you're actually shipping your source code along with the web server pre-configured and ready to use. So let's start your first container. Head to your terminal window, and from here, you can do a docker run hello-world. Docker will now pull the image from its registry and run this image. You should see a welcome message from Docker. This image contained an operating system and contained a txt file. Once the container was started, it outputted the content of that file. That's it. You've just run your first container. Congratulations! To get a better feel of what just happened, let's try another example. First, let's output some content into a file. Using your editor or with an echo statement, you can create a file called hello.txt. This file will have a simple message saying hello. And now we can use the Alpine image, which is a minimalistic version of Linux that is great for small containers. Let's start by using a docker run command again. Now you will mount a volume. What this means is that you will take a folder from your local machine and map this into a folder accessible from within the container. In this case, you will take your current working directory and map it to the /app folder inside the container. Next, you can tell Docker to run the Alpine image. Finally, you specify a command that you want to execute once the container is started. In this case, you can ask Alpine to use the cat command, which is a command in Linux that prints a file to the standard output, to show the content of the hello.txt file. The result should be a line that says hello from the container. You can also log inside a container by running Docker in interactive mode with the -it flag. Say you want to see the content of the file system inside of our container this time. You will use a very similar command. First, we will use docker run. With the IT flag, we will mount our volume just like we did previously. It will still be the Alpine image, but this time we will execute /bin/sh to open up a shell session instead. You now see the /hash, which is the prompt from our shell. From here, you can cd into app and you can view the content of the hello.txt file. To exit this session, you can use the command exit. Containers can be very useful to emulate various environments. You can also use much more complex containers. In this case, we had a container with a simple operating system, but a lot of containers will include a bunch of executables and runtimes. You could, for example, start a container that has the latest version of Node.js installed by running an image called node. Just like in our previous examples, you can specify a command to be executed once our container is started. In this case, you will ask Node.js to evaluate the following statement: console log process version. This will start the container, execute the command, and you should see a version number as the output. Note that if you run node-v in your local environment, you might have a different version number. This is because the runtime for Node.js that ran that first command is not the same as the one that you have installed on your machine. In fact, you don't even need to have Node.js installed at all to run Node as long as you have Docker. This can be very useful if you want to share your code with another team for testing purposes. It doesn't matter what runtimes they have installed on their laptop. By using a Docker command, you'll be able to specify what runtimes to use to execute your code. Another neat thing that you can do with containers is to pass environment variables to your container. This way, you could pass it something like the base URL for your API. Your development team would then be able to use a different API than your production server. To pass an environment variable to your container, you can use the -e argument. In this next example, we'll use a docker run. We will use the -e flag to specify an environment variable called name, and we'll call it world. We will use the base image node latest, and we will run node-e to evaluate console.log hello plus process.env.name. And this is how you access an environment variable inside a Node.js application. If we run this, we should see the output hello world. If we take that same example, but change the environment variable here to Joel, you should see hello Joel. Here's how you can run a database using a container. First, you will use the same docker run command we used for the previous example. Next, you will need to map some ports. In this case, we are telling Docker that any request incoming on port 3306 will be mapped to the port 3306 inside the container, which is the default port for MySQL. You'll want to run this application in detached mode, which means it will run in the background. To do this, you add the -d flag. You'll also eventually want to interact with this container, so you'll need to give it a name. You can use --name to do so. Next, MySQL will need a few environment variables to configure itself when it starts. You will need to add values for the user by using the environment variable MySQL user. We will add another environment variable for the password by using MySQL password equals MySQL. You can also add a root password by using another environment variable called MySQL root password. We'll use root for now. And finally, you specify which image you want to use. In this case, we'll be using MySQL 5.7. You should then see a long hexadecimal string. This is your container ID. To validate that your container was started, you can use the command docker ps. This will list any running container you currently have. You can see some basic information here like the ports that were mapped, as well as the name of this container. If you want to stop this container, you can use the very first few characters from the ID or the actual name of the container with a docker stop command. If you run docker ps again, you will notice that there are no more running containers. You can now restart this container with the previous command that you typed in. Now you should be getting an error. This is because we're trying to start a container called casecourse-db, but we already had a container with this name in our internal registry. To restart this server, you will need to remove the previous container first by using docker rm casecourse-db. And now, restart the container with the previous command again, but this time, add the --rm flag. This will take care of automatically removing this container once it stops. You now have a running MySQL server on your machine. Everything came pre-configured for you, and it just works out of the box. If you share the same command with your team members, they will be able to run the same database. Now we can go back to our backend again and start that server. Our server is now running, so if we open up a new tab and we do a curl on localhost 3000/help, we can see that there's another error message. Well, I guess we're making progress, as this is a different one this time. This time your server is complaining about a missing database. And that makes sense. We are running a fresh install of our database right now, so there is no data in there. Here's a neat trick. A lot of containers will have a folder from which any file present will be executed before actually starting the server. In this case, any .sql file in the /docker-entrypoint-initdb.d folder will be executed against our MySQL server as soon as the container is started. If there were any .sh file in there, they would also be automatically executed. In the DB folder of your application, there is a .sql file. This SQL script will create a database, add the necessary tables for our application, and pre-populate the table with a single entry. You can view the content of the file by running a cat init.sql. In order to put this init.sql file in the folder that MySQL will use to populate the database, we will mount a volume with a -v flag. But first, let's ensure that our MySQL container is stopped. And let's go back to our server. Then you will need to tell Docker to use the init.sql file and map it to the Docker entry point initdb folder of our container. Using the previous command, you can use the -v flag to mount your current working directory /init.sql into the /docker-entry point -initdb.d folder into the init.sql file. Our container is now started and should be pre-populated. Let's go back to our backend server again and try to run our server. Open up a new tab. Let's attempt a curl on localhost 3000/help. You should now see a server status JSON object that shows the database as being true. If you stopped your front end previously, you can now start it again. Let's open up a new tab, go into our front, and run npm run serve. Now point your browser to localhost 8080, and you will see the running application. You should immediately see an entry on the home page for an image with no caption that has the label hello. If you go to the Generate Meme tab, you'll be able to enter a keyword and see a random image. You can generate a new image from here, or you can add a caption and hit the Captionize button. This will send a request to the Node.js server to decompose the GIF and recreate it with the caption you've just specified. Finally, you will have the option to save this to the gallery, which will add an entry to the database. One last thing about containers. They are ephemeral. They are meant to be easily disposed of, and once you stop them, no changes that you did to them will be saved. If you go back to your terminal and restart the MySQL server with the exact same command, this will restart a server with a brand new database with the initial set of data specified in the init.sql file. Check your server and make sure that it is still running. And now go back to localhost 8080 and refresh the page. You will see that any image you saved previously now has disappeared. This is great for testing since you always start fresh, but it is a problem for your production server where you'll want to persist this data. You can mount a volume that will contain your database in order to save this data, but this will be tackled in a later lesson. So congratulations, you've now started the application. In this lesson, you use Docker to start a MySQL server and your application is now connecting to it. All of this without actually having to install MySQL. Hopefully, you can start seeing how containers can be useful by now. In the last session, you started a MySQL server by using a container that you pre-configured with everything needed to run this server. You used an image that was pre-built by the MySQL team. But what happens if you want to share your own image to be shared with your team? This is what we will see in this lesson. You will learn how to create your own images that will include all the source code of your application, along with a specific version of Node.js and all the dependencies that are needed. Once you are done, you'll be able to share this image with other people, and this will ensure that everyone is running the same environment. It will even let people that don't have Node.js run the server. This will also have the added benefit of cleaning up everything once you close the application. If you tried to create a few memes in the last lesson, you'll notice that you might have a bunch of files in your temp folder. These are the files that are created during the process of extracting the frames and regenerating the caption GIF. When we will run this application inside a container, all of this will be cleaned up as soon as we stop this container. The first thing you'll want to do in order to prepare your application to run into a container is to identify any variable that could be stored in an environment variable. This would be any value that would vary based on where the code is running. Examples of this would be a base URL for your API. It would most likely be different from your production environment, test environment, and development environment. The same could go for log files, or in the case of this application, the database configuration. Thankfully, the software developer that worked on this project isolated those variables in a file called config.js, so you won't have to dig too far. For each of the values in this file, you can change it to use a matching environment variable. You can leave the default values there for now by using a OR operator that double pipes. This way, if your application can find an environment variable, it will fall back to the default values, so your application will still run locally without adding those variables. Another variable that could change would be the Giphy API key. This value will need to stay a secret, but you'll want your server to be able to download the code from your repo and run everything. By storing this value in an environment variable, you would be able to keep it a secret and store this value on the server instead of in your source code. This variable is found in the API keys file. Now don't put in a default value here. This will let you go into your gitignore file and remove the API keys line. This file will now be added to your repository and will rely on an environment variable to get the value of that API key. Next, you will want to create an image that can then be shared with the rest of your team. To create your own image, you will use a dockerfile. This file will describe how the image is to be created. It will list a series of layers to create your own custom image. First, you can go back to your backend directory, and from here, create a file called dockerfile. You can now open up your code editor and start working on that dockerfile. A dockerfile always starts with a from statement. This tells Docker what base image to use and how to build on top of it. For your backend, you will start with a from node 14. This base image contains both the node executable and npm. Next, you will specify a working directory for our application. This could be anything. In our example, we will use /app. Next, you will also need to create two subfolders that are used by the application. The run command will let you specify a command to be executed inside the container. Note that those two folders will be created inside the /app folder since we specified this to be the working directory in the last step. Now you can copy both your package.json and package.lock.json files. Then you'll run the npm command to install all the dependencies needed by your application. Note that you are only copying the package.json file here and not the entire directory. This will allow you to create an image that takes full advantage of the Docker layer caching, and this will significantly speed up your build process. Now that the dependencies are installed, you can copy all the code and assets that are required for your application by using the copy statement. And finally, you will need to specify which command is executed to start the server. Up until here, all those commands are executed to create your Docker file. The next command will be the one that will be executed when you use that docker run command. In our case, the main file for this server is /app/index.js, so you will use the command node/app. You now have a set of instructions that Docker will use to create your image. In order to start this image build, you can use the command docker build. You will also need to name your image. To do so, you will use the -t flag to specify a tag. You can also add a version number after the name of your image if you'd like. If you don't, it will automatically append that latest tag as the version number. Finally, you need to specify the path to the Docker file that you just created. In this case, this is locating in the current working directory, or dot. You should now see each of the 10 steps being run and see a message telling you that the image was successfully built. You can now test this image with a docker run command. This will be very similar to the containers you started in the previous lessons. First, you will use docker run. Then you'll need to map some ports. In our case, we'll map the port 3000 to the port 3000 inside our container. Then you can give it a name, so we'll use --name back. Next, you'll want to run this in detach mode with the -d flag, and you'll want to clean it up once it closes with the --rm flag. Finally, you can use the name of the image that you used in the previous step, kscors-back. Now try hitting your API to make sure that it is running. You can do that by opening up a new browser tab or by using a curl command to localhost 3000/help. Well, either way, you should be getting an error. It seems like the server isn't started. Because the container is running in the background, you could never see the detailed error message. The server actually crashed. You can stop Docker by using docker stop and then validate that nothing is working anymore by using the docker ps command. This will list any running containers that you have on your system. You might have the kscors-db container still running, but you shouldn't have the kscors-back container. To see what happened, you can execute the docker run command without the -d flag. The container will now output everything that the Node.js application would output in the same standard output. To see it, we can open up a new tab, do our curl localhost 3000, and go back to the original tab, and you can see here the full error trace. You can see that the error starts and outputs an error of type econ-refused. Does that remind you of anything? We're back to the start, it seems. The Node.js backend application can't find a database anymore. This is because the container is looking for a database on localhost. But localhost in the context of the container only has the backend service in it. Let's stop this container from running. You will now need a way to tell your application how to connect to the database by using a network. And this is what we'll see in the next lesson. In the last lesson, our backend stopped working again because it couldn't find a database. That might seem odd, especially since we fixed a similar issue in our previous lesson. Well, it actually makes a lot of sense when you think about it. One of the advantages of running containers is that they run in isolation. As far as the container is concerned, nothing exists outside of it. It behaves as if it was its own operating system. This is why the backend can't find a database on localhost. The two containers are running in the same host, but as far as the backend is concerned, there is no database. The same goes for the database. It can't see anything outside of what is running inside its own container, therefore it can't see the backend application running. This is great for many reasons. First of all, it prevents your containers to access the host operating system. If something happens inside the container and crashes it, you can simply restart it. Nothing can happen to the host machine. It also helps to prevent unwanted communication between various containers that might be running on your host. You might have multiple databases running, but you won't want all of your applications to have access to all those databases. Containers will prevent this. Yet, sometimes you want your containers to be able to speak to each other. And this is where container networks can help you. To demonstrate this, you can start by running two Alpine containers. Use the -it flags to run it in interactive mode and the -d flag to run it in the background. Make sure to add the --rm flag to clean it up afterwards. Give it a name, you can use 1, and the base image you will use is Alpine. And we will ask Alpine to execute /bin/sh once it starts. Because the container is running in interactive and detached mode, this will open up a session in the container and it will prevent it to close until we use a docker stop command. You can also start an identical container called to. Now that you have those two containers, you can use a docker exec command to log into the first one. You will use the -it flag to run this command in interactive mode. Specify the container on which to execute a command, this will be container 1, and specify the command to be executed. We execute /bin/sh to open up a shell session inside the container. You are now inside the container. From here, if you try to do things like ls, you will see the content of the file system of this particular container. If you try various commands that would normally work on your laptop, they most likely won't work. For example, you can try to run docker ps to see what are the containers, and you will get an error message saying that docker is not found. Once again, this is because your container is entirely isolated. As far as this container is concerned, Docker was never installed. The Alpine image comes with a very limited set of tools and is ideal for lightweight images. It comes prepackaged with ping, which is the only one you will need for now. Docker took care of networking your container to the outside world using your network interface. This is why you can ping various services from inside the container. So if you want to reach the redhat.com website, you should see the response time when you're using ping. You can use Ctrl+C to stop the ping command. If that works, you should be able to ping the other container, right? That would make sense. Try pinging the other container called to. You will get an error message. Once again, as far as this container is concerned, the container name 2 does not exist. You can exit the shell section with the exit command, and you can stop those two containers from running now. Now, we need a way for those two containers to be able to talk to each other. Docker has a tool called networks to help you with this. The first thing you'll want to do is to create a network. A network will create a group of containers that can talk to each other. To create this network, you use the docker network command. Use create to create a new network and give it the name Alpine network. Now every container that we add to this network will be able to see each other. You can add a container to this network by using the --network parameter in the docker run command. Do this for 2 Alpine containers that you had running earlier. Your 2 containers are now running and are part of the same network. You can see the network configuration with the docker network inspect command. From here, you can see the containers that are part of this network along with their internal IP addresses. Now let's log back into the container called 1. From here, you can try to do a ping to the container called 2 again. And you should see that the container is successfully pinged. Docker added the name of the containers to the internal host list, so you don't even have to learn the IP addresses of the containers. You can reach them by their own name, which makes it a lot easier to be able to get all of your microservices to speak to each other. You're now ready to apply those same principles to your application. First, start by creating the K-Scores network. Then, start your database with the additional --network parameter. And finally, start your backend with the same --network parameter. If you try to reach the /health route, you're still getting an error message saying that the backend can't connect to the database server. That's because the API tried to connect to a database on localhost, but it actually now runs in a container called K-Scores-DB. Remember how we added an environment variable for a database server? This is where it will come in handy. You can restart your backend by adding it the -e parameter to pass in the name of the database server. Note that this container was running in detach mode. If you want to verify that your containers are indeed running, you can use docker ps. And if you want to see if there are any error messages in your backend service, you can view the logs with the logs command, followed by the name of the container. If everything worked, you should see a message saying that the server is running. Now that you have a working database and backend, it's time to go back to our front end and build another container to serve those files. In the last lessons, you saw how to use containers and how to create one for your backend. Now's the time for more advanced container images. In this lesson, we will actually use a container to build our container. This is called a multi-stage build. For your front-end, a Vue.js application has been created from the CLI. Vue.js, just like React and Angular applications, have a development mode as well as a production mode. When you started the front-end at the beginning of this course, you've used npm run serve. This is a development server that is built with Node.js. It watches your files for changes and it's optimized to recompile the application and refresh your browser automatically. When you're building a React application, you have a similar setup. You can use the Create React App CLI tool to build a skeleton for your application. This skeleton will include not only the base files for your application, but also a full development environment with a server that watches your files for changes and refreshes your browser automatically. These tools are great for development purposes. It makes it much quicker to see the resulting application and is way better suited for debugging. Once your application is ready to deploy though, you won't want to use the same setup. This development environment is somewhat slow and has a lot of code that is not used. There's no need to watch your files for changes in production. They shouldn't change. Ideally, for your production server, you would like to ship a minified version of your code. This will cut down the download time to see the initial page. Some build scripts will even perform tree shaking, which is a method to find all the code that is not used in your application and simply remove it. Some CSS frameworks and tooling like Tailwind can also check your code for unused classes and automatically remove them. Finally, you will want your application to be usable by the greatest number of users possible, so you might need to add in some additional prefixes to your CSS styling or some patches to support some JavaScript features on older browsers. To do this, you will need to run a script to build your production application. This script will take all of your JavaScript files and merge everything into a single minified JavaScript file. It will do the same for your CSS. It might also perform some transpiling and some other tasks like the tree shaking for you. By doing so, you will end up with a minimal set of files, typically a single HTML, JavaScript, and CSS file for a total of only 3 files to download. These files can be hosted just about anywhere. Since this course is about containers, we'll be using an nginx container to serve those files. Nginx is an open source, high performance HTTP server that will be able to handle many requests to your front end. When building our front end container, we will not only want a container that has nginx and our minimal HTML, CSS, and JavaScript files, but not the full Node.js runtimes and the source code. This is why we will use a multi-step build. The first step will use a container with Node.js to create the files. Its sole purpose is to run this build script and to create that production version, those 3 files. The second step will create your nginx server, and the 3 files that were generated in the first step will be transferred to that second container. The container that was used to generate your production files will then be discarded, and you will only be left with that second container, which is lightweight and optimized for the web. You can use multi-stage containers to perform various operations on your source code and then copy the output to the next step. You can even create your own CI/CD pipelines by running multiple steps inside a Docker build. The resulting image will only be the last image that was created, and all the additional overhead from the previous steps is discarded. In the last lessons, you saw how to use containers and how to create one for your backend. Now's the time to see more advanced container images. In this lesson, we will actually use a container to build our container. This is called a multi-stage build. For your front-end, a Vue.js application has been created from the CLI. Vue.js, just like React and Angular applications, have a development mode as well as a production mode. When you start the front-end at the beginning of this course, you've used npm run serve. This is a development server that is built with Node.js. It watches your files for changes and is optimized to recompile the application and refresh your browser automatically. This is great for development. Once you're ready to deploy this application, you won't want to use the same code. In fact, you'll need to run another script to build a production application. This script will take all of your JavaScript files and merge everything in a single minified JavaScript file. It will do the same for your CSS. By doing so, you will end up with a minimal set of files that can be served over any static file web server. In this case, you'll be using an nginx server to serve these files. Nginx is an open-source, high-performance HTTP server that will be able to handle many requests to your frontend. When building our frontend container, we will only want a container that has nginx and the minimal HTML, CSS, and JavaScript files, not the full Node.js runtimes. This is why we use a multi-step build. The first step will use a container with Node.js to create the files, and the second step will be our nginx server with the files. The container that was used to generate your production files will then be discarded, and you will only be left with that second container, which is lightweight and optimized for the web. Let's start by creating our Dockerfile. Just like in our previous examples, your container will need to start from a base image. In order to build our application, we will need Node and npm. So we can start from Node 14, and we will give it an alias by using the as keyword. Next, you can copy all of your source code over and change your working directory to the /app folder where the application is now stored inside your container. Now we can ask this container to install any dependencies and then run the npm script that will build our production version. For a Vue.js application, this will create a /app/dist folder with those static files. You now have a container with the production version of your application that is ready to go. But this Node.js container can't serve the files at the moment. It doesn't have a server built in. What you will need to do now is to create another container with an nginx server and copy the files from the first step into the second container. You can start from an nginx base image and change your working directory to /usr/share/nginx/html, which is the default folder from which nginx will serve files. Now we can copy the files from the first container into this new container by using the -- from parameter and the alias that we gave to that first step. We will take the files from the /app/dist folder, which is our compile website, and copy them into the working directory of this second container. The nginx image already exposes the port 80 and automatically starts the server once the image is started. So you don't need to do anything else. Everything will be handled for you. You can now save this image and go back to your terminal. You can build this new Docker image by using docker build. Let's give it the name katescourse-front. And the location of the path is the current working directory, so dot. You will now see the steps for both the containers being built, and that first container will then be removed so that you will only be left with that last little part, only the nginx server serving your production-ready application. Your front end is now containerized. You can start this image by executing a docker run, add the -d flag so that it runs in detach mode, also add the --rm and --name flags. We will call this one front. Finally, add a port mapping. Nginx is running on port 80 inside the container, but we will need to map into another port on your machine. So let's use port 8888 to map into the port 80 of our container. Finally, give it the name of the image to start. In our case, it's katescourse-front. Now let's open up our browser and let's go to localhost 8888. You should now see the application running. Now if you try to generate an image, it should fail. That is because I don't have a backend nor a database running at the moment. If that is also the case, you can check if your containers are running by using docker ps. If they are not running, you can start them by using the same commands that you've used previously. Now that all services are started, go back to your browser, refresh the page, and you should be able to generate a new meme. Interestingly, you didn't need to add the front end to your K-Course network. This is because the front end is living in your browser. Any requests that are made by the front end are actually made by our browser on your development machine. Those requests are reaching out to the internet, to the server called localhost. It just so happens that this server is in your local development machine. Everything should now be working. Well, almost. Once you deploy this application, there's a chance that you might want to run your backend service on another service than a local host. Let's simulate this. First, let's stop the backend server with docker stop and reuse the same command to restart it. But this time, we'll map to the port 3001. Let's refresh this page, try to generate a meme again, and our application is broken again. If you open up the developer tools, you can see that all the requests are still going to port 3000. It seems like the value of our backend was hard-coded in the front-end code. Your application will work as long as all the containers are running locally, but it will break if you move the backend to another server or to another port. To solve this issue, we will need to use environment variables inside of our front-end application. This will cause an issue due to the fact that the front-end lives in the browser and not on the server where the environment variables are stored. We will see how to solve this in the next lesson. In the previous lessons, we managed to put all of our front-end in a container, and we can now distribute this container to the rest of our team. This will work well in a standalone website, but as soon as you need to connect to an API, this could become an issue, since the URL that you use in development will most likely differ from the one in production. In order for your code to still work in production, you will need to specify the base URL of your API. As you've seen in a previous lesson, this can be done by using an environment variable. Since the value of the base URL changes between the environment that you're in, it would be the best way to actually set this. But there is a problem when you want to use environment variables in your frontend. When you use an environment variable for the backend, it works because the Node.js server is actually able to access the value from the operating system. In the case of your frontend, it lives in the browser of your end users. When the user goes to the website, it downloads the HTML, JS, and CSS and runs them inside the user's browser. That code is now unable to communicate with the server's operating system to have access to those environment variables. There are a few techniques that are often used to go around this. You could switch your backend server to a Node.js and create a route that would provide all the configuration, which would be accessible by your frontend. But this requires us to change our base image from nginx to Node.js, and to create a web server, and to change a little bit of the logic of our application. You could also use something like PHP or another server-side rendered language to change the HTML content before it gets served. But once again, this requires a lot of changes in the way our application is built. Thankfully, there is another way to do everything through a Dockerfile. We're already using Docker to initiate our build process. By adding a few commands, we can change those variables to something more generic in our build process. And then, just before our server starts, we can inject the environment variables into our configuration. This way, we don't need to change anything in our development environment, and we can keep our nginx server for high performance and small footprint. To do so, you'll need to put all your configuration into a single config.json file to make it easier to override those settings. Next, you can use a bash script to override them as part of the Docker build step. And finally, you can use nsubst to overwrite the environment variables with the actual values just before the server starts. If the environment variable changes and the container is restarted, it will take into those new values and send those to the end user. In the next lesson, you will see how to do this in a somewhat naive approach. It will look for hard-coded values such as localhost port 3000 and simply override them by using sed, a Linux CLI tool to edit some text in a file. The new value of that JSON property will be the name of the environment variable. In this case, $base URL. This will let you use the env subst on the file to change the name of the variable into the actual value of that variable. This will work perfectly well in the context of this application and can work for you if you have a single value that needs to be stored in an environment variable. The lesson after that will show you how to use JQ, another CLI tool, to change the values inside the JSON file. This time, you won't rely on a hard-coded value, but rather on the property of the JSON object. This will make for a more future-proof container, but requires a little bit more work and some bash scripting. So feel free to skip that lesson if you don't want to dig deeper into this topic, but if you want to build future-proof containers and front-end containers that can access environment variables, you should probably look into it. The first thing you'll want to do is to find out where this was coded and make sure that it is only defined in one place. If you do a search for localhost 3000, you will see that it is only defined in one place. That's good. Half the work is done already. You will only need to modify the front/source/config.json file. But this value works well in our local environment, and maybe other developers in our team are using different values. For this reason, you will leave the value hard-coded in here. You'll only change it as part of the build process in the Dockerfile. To do so, you will use a bash command called sed. Sed is a Linux utility that can be used to substitute some text in a file. Now head back to your Dockerfile. Right after the copy statement here, let's change the working directory to /app/source. From here, we can run our sed command with the -i argument, and we're going to specify what value we are going to change. In this case, we are looking for http://localhost 3000, and we will substitute this with $base URL. All of this will be done in the file config.json. The result of this operation will be to actually change the config.json file to have a base URL here on the server, inside the container. This replacement works well when there's a single environment variable, like in this example. However, if you want a solution that is more future-proof, this will be introduced in the next lesson. Now that your configuration has been changed to a generic value, you can run your npm install and build scripts. This will create all the minified CSS and JS files with the generic value. The next step will happen in the next step of our container. Just before the server starts, you will need to override this base URL in your JavaScript package with the actual value of the base URL environment variable. In order to do so, you will need to bypass the command that the nginx base image uses to start the server with a different start script. This new script will use the env subst command that is included with this image to substitute the base URL string with the actual value of it from the image environment variable. Now, when you will start the container with a -e flag, it will take this value, override the $base URL string in our JavaScript file. Once this file is served to the browser, it will now contain the value from the environment variable. To do so, you will write a small bash script. This file will be called start_nginx.sh and will be in the front folder. First, the script will run through all the app.something.js files and rename them to app.tmp.js. Then, for each of these .tmp.js, we will use the env subs to replace the environment variable $base URL with the actual value from the container environment variable. The output from the env subst command then pipes to the original file name. Once all the JavaScript files have been modified, you can start the nginx server with the nginx-g command. The final step, as far as our container is concerned, will be to copy this bash script into the container, change the permissions on it so that it can be executed, and change the entry point of your container. An entry point is a command that is executed when the container is ready. It's usually the command that starts your container. There can only be one entry point in a container, so by adding it here, you are overriding the default entry point that was defined in the nginx base image. You are now ready to rebuild the frontend image and start all three containers. To rebuild the frontend, go to your front folder and run the docker build command. You can now restart all of your containers to see those new changes. First, stop all the running containers, and then start your database container from the db folder. Also start your backend. This time you can also start your backend on port 3001 as you did previously. And finally, start your frontend server, and this time add the environment variable base URL to point to localhost 3001. Now open up your browser and point it to localhost 8080 again, and you should finally be able to try out the application. Everything is working again. And if you change any of the server ports or URLs, you will be able to use an environment variable to specify the new values, and you won't need to change your code. Also, those values such as the Giphy API key won't be in your repository and can be kept a secret on your server. You are now almost ready to deploy those images to a server. Before you do so, you will have to ensure that these images run on any server. Right now, those containers are running as a root user inside their context. If you open up a bash shell and run the whoami command, you will see that you are running this session as the root user. You will need to do some small changes to your Docker files to ensure that you're not running as root anymore. But this will be done in one of our next lessons. You saw how to use sed to override the hard-coded path to the API. This works well when there's a single value to replace. Now, if one of your team members replaces the value of localhost 3000, your build will break. There is a better solution to this, but it involves adding a new software into that first container. To change this value, we will use JQ. JQ is a command line tool that makes it easy to change values in a JSON file. The base image that we used for building the application does not contain this tool. But that is not an issue, because a container is essentially just like a Linux machine. You can install software in your image and use this tool to perform various operations. To install JQ, you will need to download the binary. To make it easier to eventually upgrade, if there is a security vulnerability of some sort, you can add the version number as an environment variable. You can specify this variable with the env keyword. JQ version equals 1.5. Next, you can download JQ from the GitHub repository as shown below. Note how the JQ version environment variable is used in the URL. JQ will be downloaded using wget, which is already installed in the base image. You will also need to specify wget to ignore certificates, add the URL to the GitHub repository, and then you need to tell wget to output this URL into a file in the /temp folder. Note that this is a capital O. Next, you will copy this binary file into the /usr/bin folder. Finally, you will need to change the permissions on this file to make it executable. Now that JQ is installed, you will be able to use it to change the value of the base URL property in the config.json file. You can do so with another run statement. First, we will execute the following command. We will tell JQ to change the property base URL in our config.json file to the value $base URL. This is done in the config.json file. We will then store the output of this command into the contents variable, and we will echo that contents into the config.json file to overwrite the config.json with the new configuration. Finally, you can remove that sed command as we don't need it anymore. The nice thing with JQ is that you only change the value of one of the JSON properties. If your developer team added more configurations to this file, the script in the Dockerfile won't change the rest of it. This makes it a safer way to change only the values that need to change in the configuration. You could also add more JQ commands to overwrite other values in the config.json file, should you need to override them with environment variables. This makes your Docker file a little bit more robust, more future-proof, and more ready to be used in production. So far, you've managed to get all your containers running on your local machine. That is great for your development environment, and you're almost ready to start sharing those images with your team and to deploy them on a server. While the risks are very limited in your own environment, you will need to have security in mind when you're deploying those containers to a production server. Some hosts will prevent any containers where the user is root to be running at all. The containers you built in the previous lessons are running as root for a few reasons. First of all, we read and write files from the file system in order to install tools like JQ or to change some configuration files. And second, we are running servers on ports that are restricted to the root user, such as port 80. You can start by modifying the Dockerfile for the backend service. Because we are using a node-based image, there is a non-root user available for us to use. This user is called node and is part of the node group. In the current iteration of your Dockerfile, you start with the node-based image and then switch to a working directory named /app. Docker will create this directory if it doesn't exist, and the owner for that directory will be root. In order to give the necessary permissions to user node, you can add a command to manually create this folder and then change the ownership to node. Once the directory is created and the working directory has been changed, you can tell Docker to switch to the node user for the rest of the commands that are executed in the Docker file. All the subsequent commands will be running as non-root user called node. The last change that you will need to do is to the copy commands. You will need to ensure that the ownership of the files that you copy from your file system into the container is actually the node user. You can do so by adding a --chown equals node to the copy commands. The image for your backend is now completed. It now has everything necessary to run in any environment and is now more secure as it runs as a non-root user. The code in it will also rely on environment variables to specify things such as API keys or the database host, username, and password. It is now time to tackle the front-end container. This container uses two steps. The first step uses a container to build a production version of your Vue.js application. This container won't be deployed on a server. Its purpose is to create the necessary files for the second step, and then we don't use it anymore. The nginx server is the one that we will need to run as a non-root user. To do so, you will first need to change the nginx configuration. Start by creating a file in the front folder called nginx.conf. Now open up your editor to modify this file. First, you will need the basic required configuration parameters for an nginx configuration file. Without going into the details of all the different steps, this is what is the strict minimum required to start your nginx server. Next, you will need to change the server settings to run on port 8080 instead of the default port 80, which is restricted to the root user. You can do so, a listen option in your server object to 8080. You can also change the default path that nginx uses to serve files from. In the location object, type root for the root folder, and we can do /code, which is a directory that we will create, and give the necessary permission to our users. Now that you have a new nginx configuration file that will let the server run as a regular user, it's time for you to edit your Docker file one last time. This modified container will run as user nginx. In this case, the nginx base images provides us with a non-root user. In many cases, you will see user 1000 being used. This is an arbitrary number. You could use just about anything, or even create a user with the user add command. Using user 1000 is a standard way to do this in Docker when a non-root user is not provided. In the second step of your build, right after you specified the from statement, you can copy your new nginx configuration file to override the default one. Then, similar to what you did to your backend, you can create a /code folder using the mkdir command and change the ownership with the chown command. You should also change the file permissions to 755. Next, there's a series of files and folders that nginx needs access to in order to run. You can change the ownership of all of these folders in a single run statement using ampersands to change those commands. Nginx also requires an nginx.pid file. This file does not exist yet, so you need to create it and assign the ownership to the nginx user. Finally, you need to change the group to those files and folders as well as change the permissions so that nginx can read and write to these folders. You can do this with a last run command. Change the group, var cache nginx, var run, var log nginx, var run nginx.pid, and change the file permissions with chmod to 755 to those same folders. As you're changing all permissions in the file system, you can move the lines from your original Dockerfile that copied the start nginx file right in this section. Now that all permissions have been adjusted, you can tell Docker to switch over to the nginx user using the user statement. You can then remove that workdir command and copy the files into the /code folder. Also make sure to add the --chown flag to the copy statement so that the files will be writable by the nginx user. Finally, you need to tell Docker that this new image uses a different port. To do so, you will use the expose statement for the port 8080. This is done just before you start the server with the entry point command. Before you rebuild this container, you will also need to change the start_nginx.sh script. The files are no longer stored in this directory and are now stored in /code/js/appstart.js. You are now ready to rebuild those two containers and start everything again. From the front folder, run a docker build with the name kscores front and dot for the current working directory. Then go to the backend folder and run that docker build again with the name kscores back. Use dot for the current working directory. And you are now ready to start all of your containers again. You can use the same commands as you did previously. When starting your new front-end container, don't forget that you now need to map port 8080 instead of the port 80 as you did previously. Once again, you can point your browser to localhost 8080 and everything should be running again. But this time, everything is running as regular users, making it more secure. Furthermore, this will make it easier for you to deploy on various servers, as some of them would have blocked your containers running as root. Now that you have everything containerized, you will need to share these containers with the rest of the world. And that is what we'll do in the next lesson. The base images that you use to create your own images all come from such a registry. When you use the node image, it was available because someone initially took the time to create a Docker file and push it to a registry. Many registries are available for you to push your images to. Docker Hub is a popular registry. In fact, If you are using Docker, the base images were pulled from Docker Hub. There are also registries, such as Quay, that you can install on your own infrastructure, so you can keep all the images pushed to it private. In this course, you will be using Docker Hub. It offers to store unlimited public images on the free tier. To create your account, just head to hub.docker.com and follow the instructions. Once you have an account created on Docker Hub, you are ready to store your images. The first step will be to log in the registry using the docker login command, followed by the name of the registry you want to connect to. In our case, this will be docker.io. You will be prompted for your username and for your password. Once you are logged in, you should see a message confirming that you are indeed logged in. Now that you are logged into Docker Hub, you will be able to push your images to the registry. In order to push the images to the registry, you will need to rename the images to registry/username/image_name. Because Docker assumes docker.io as the registry, you can simply rename the images to username/image_name. You can use the Docker tag to rename your images. My username on Docker Hub is Joel Lord, so I will rename the images accordingly. You never created an actual image for your database. The image that you're using is the base image from Docker Hub, so no need to rename or to upload this image to the registry. You will only need with the two images you recently created. Now that your images have been renamed, you are ready to store those images on the registry by using the docker push command. You'll need to pass in the name of the image as an argument. This operation will take a few seconds as every layer of your image is sent to the registry. A layer is created for each command in your Docker file. Docker will always try to reuse those cached layers whenever possible. So the more you use Docker, the quicker those pushes will become. Now that the images are pushed to a public registry, anyone can download these images on their system by using Docker pull. Once they have the image downloaded, they can use Docker run to start each container just like you did in the previous steps. Just like your code repository keeps a history of all your code changes, your container registry will keep a history of all the images. When you do a Docker push, the registry will automatically append a :latest tag to the image. When someone does a pull of your image, Docker will always pull the latest tag. This can be useful, but sometimes you will want to ensure that everyone is running the same version as your container. You might have noticed that for the base containers, there was always a tag specified. For our node base image, you use node 14. For your nginx image, you use nginx 117. By using a tag version of the image, you're ensuring that everyone will be using the same version of that image. Should you have omitted the version number in the node base image, version 15 would have been used as this is the version that is used in the latest tag at the moment of this recording. In the same way, you can and should always tag your images. To tag them, you can use the docker tag command and tag your current images to a version number. Once the images have been tagged, you can push them again to the registry. If you go to Docker Hub, you will see the images that you pushed. And if you click on any of the images, you will see the details, including the versions that are available. This will be useful when you want to share your entire containerized application with your team, and I'll show you how to do that in the next lesson. Now that you have everything stored in containers, you will want to share this entire 3-tier application with the rest of your team. So far, you've been using the command line to start manually each one of the containers. And you've seen how these instructions can get complex. Now this works in your local machine, and you could even write some scripts to start and stop those containers. But there is an easier way. This is where Docker Compose will come into play. Docker Compose is part of the Docker tool suite and is an application that will take a YAML file to start all of your containers with one single command. The first thing you'll need to do is to create a file called dockercompose.yaml at the root folder of your project. This is where you will define all the containers that are used by your application. In this file, you will start by telling Docker Compose the version of the API to use. You can use version 3.8 here. You will also define all the services or the containers that will be in your application, as well as all the networks. You can start by defining a database service. Before we start describing this service, let's take a look at the original command that we used to start this container. You will want to reproduce this command line inside your YAML file. The first step will be to give a name to this service. We will call it kscores-db, just like the name that we gave in our command line. We then specify the image to be used. The image will be mysql 5.7. So we can already remove this one and the name. Now let's proceed with each one of the other parameters in our command line. The -d flag can be omitted because it will automatically be done by Docker Compose. So let's copy those. For the ports, we will add a port property. This will take an array, and our first element in the array will be the ports that we've just copied from our docker run command. Now let's move on to the environment variables. This will also be an array to which we will pass each one of the environment variable that we had defined previously. We can ignore the --rm as this will also be taken care of by Docker Compose. And we are up to our volume. Volumes will also be an array in which we will add the volume that we had before. Now we won't be able to use the current working directory, so we will simply use a directory relative to the path in which we are. And finally, we will need to specify the network that we want to use. This will be in the networks property, which is also an array, and we will specify the name of the network. That's it. We've just reproduced our full Docker run line. Now that you've defined the database server, you can define the backend as well. Once again, let's start from the docker run command, just like we did for the database. The name for this service was back, and it used the image joelord/kscores-back version 1. So we've taken care of the image and the name. We can now mount the ports. --rm is taken care of. Let's create our environment variables. We can add the network. And we can ignore the -d as well as the docker run command. Finally, you can do the same for the front end. The container was called front. The image that was used is joelord/kscores-front version 1. The ports were 8080 mapped to port 8080. We also had some environment variables, more specifically the base URL, mapping to HTTP localhost 3001, this one right here. And we had no need for a network. And that's all we had for our front end. The last thing that we will need to do is to tell Docker to create a network so that our components are able to use it. The name of our network is kscores, and we will keep all the default parameters so we can just leave that empty object right here. Now that your Docker file is completed, Docker Compose will be able to use this to start all the necessary containers and run your application. From the root folder, use Docker Compose up. This will start all the services at once. You will see the logs in real time for each one of your services. Just like when you run a Docker run command, you can use the -d flag to run all the services in detach mode if you'd prefer that. To stop the services, you can use Ctrl+C if running when the logs open, or with Docker Compose down if you're running everything in detach mode. You can now send this Docker Compose YAML file to another laptop that has Docker installed. From this other machine, you can run the Docker Compose up command, and Docker will automatically download all the required images, configure them, and start all of your services. It doesn't matter how the other laptop is configured, if it has Node.js installed or MySQL, it doesn't matter which operating system it's using, the application will always run the same in any environment. So far, we've focused mainly on how to use containers in a development environment. You now know how to use containers and even how to build your own if needed. You've also seen how useful they can be and how easy it can be to share multiple services with your colleagues.